Alright, everyone, so welcome back. So in this video, we're going to solve a PDE with auxiliary conditions. So you need to find the solution such that it satisfies this equation, but also that satisfies the given condition, so our solution won't be general. Now, this is a homogeneous linear solution. By the way, if you're following the Strauss textbook, this is actually section 1.2, example number 1 on page 7. So in case you're following that book, that's where this example comes from. That's the book that I used when I took this class. Let's see, so this is a homogeneous PDE with constant coefficients. So its solution should look like the following, right? And it's going to be some function bx minus ay. So it's going to be negative 3x minus 4y. So from here, you can do two things. You can go ahead and find the solution using this function, some function using negative 3x minus 4y, or you can use that one technique that we use where you can factor out a negative and find a new function. I'm going to do it both ways just so you can see you get the same result, but it's actually easier you factor out a common factor. So it's this case, or you can also use u of xy. I'm going to call a different function, maybe g. So g of 3x plus 4y. Right, in this case, I removed the negative, factored out the negative from both of them, and I got a new function, g. But let's do it this way first, where we have, this actually takes longer. So this is our general solution, but now we're looking for a specific solution that also satisfies our auxiliary conditions. But we are given these conditions for a reason. For example, you can set x equal to 0 and use it here. So we can say, okay, u of 0 comma y. We substitute in 0 for x. So we would end up with, right, that goes away. We end up with negative 4y. But we know that u of 0y is equal to y to the power of 3. So we can make that substitution here as well. So I'm going to actually substitute this in for u of 0y. So now we have y to the third equals f of negative 4y. We want to write our function in terms of one variable so we can make a substitution later. In other words, you find a dummy variable to take its place for y and get this in terms of another variable. So then we can substitute this expression back into it. Or pick a dummy variable, so let w equal negative 4y. Solve for y. So that means y is going to equal w over negative 4. We replace where we see a y with w over negative 4. So we're going to get, let's see, w over negative 4 to the power 3 is equal to f of w. Now we can go ahead and replace our solution. Replace w with our negative 3x minus 4y. So that means f of to the power of 3. We can factor out a negative from both of them. So that's going to be negative 3x plus 4y over negative 4. And that's all going to be to the power of 3. It's equal to f of negative 3x minus 4y. The negatives cancel out, and you can distribute the 3 to top and bottom of your fraction. So we get, just scroll this up. So we end up with 3x plus 4y over 4 to the power of 3 equals f of, and we distribute 3, so we get 64 3x minus 4y to the power of 3 over 64 equals f of negative 3x minus 4y. But notice that we said this is equal to this, but transitivity up here we said that u of x equals to the following expression. So we can say that u of x, I'm going to rewrite it, I'm going to switch these around. So u of x, our function that satisfies this PDE along with the auxiliary conditions should be the following, and we'll check that in a bit. It's going to be 3x, I should be plus 4y over 64 to the power of 3. Now, so that one takes a little longer because you have to deal with the negative, but let's say instead we didn't go with this expression, but instead we went with, so we didn't go with this expression here, but we went with this expression. So a very similar process. You would substitute in 0 for x. So u of 0 is going to be g of 4y. But we know that u of 0y is equal to y to the power of 3, so let's make that substitution. Again, all we're doing here is finding the specific equation that not only satisfies this, but also the auxiliary condition. So again, this one satisfies the PDE, but now we're doing all this extra work to find the actual expression that will give us y to the power of 3. So let's see, y to the power of 3 is equal to g of 4y. Similar as before, we let w equals 4y. That means y is equal to w over 4. Plug those back in. Substitute those back in. So we end up with w over 4 to the power of 3 equals g of w. Now that it's in terms of a single variable, we can make the substitution. Replace that. Again, I'm going to switch these around now because then it gets kind of annoying later. So g of 3x plus 4w is equal to 3x plus 4 y over 4 to the power of 3. Distribute the 3 to both the numerator and the denominator. We end up with g of 3x plus 4y equals 3x plus 4y to the power of 3 over 64. But we know that g is equal to u. So place that with u. So u of x, y equals 3x plus 4y to the power of 3 over 64. So in either case, we get the same solution. As I said before, I just prefer this route because this way, you get rid of all these negatives you have to worry about, and you avoid any possible miscalculation on there. As you can see, this should be our solution. Not only satisfies, they're the same, but this should be 64 actually. Forgot that. But this expression should satisfy this PDE along with the auxiliary conditions that were given to us, and we can check that right now. Let's see. So let's see, our PDE was for u of x and the auxiliary conditions. So that was our PDE and those are auxiliary conditions. And we said that our solution is actually u of x we're saying that that expression, that function satisfies the PDE along with that auxiliary condition. So let's check auxiliary conditions first. So check auxiliary. Is it true that if I plug in 0 into this expression, I would get y to the power of 3? Let's find out. So u of 0 to the power of 3, u of 0y is equal to, let's see, 3 times 0 plus 4y plus 4y to the power of 3 over 64. That's going to give us 4y over 64 to the power of 3, which gives us 64y to the power of 3 over 64. And yes, in fact, it does equal to y to the power of 3. So it does satisfy the auxiliary condition. Now that it satisfies the PDE, remember in the previous video we said any function where the expression is dependent on bx minus ay will satisfy, but we can check here. So now let's do that. I'm going to check the PDE. Let's see, so u of xy is actually equal to 1 over 64 3x minus 4y. I wrote it like this because it makes it easier to see the chain rule in action. So bring down the 3, then multiply the derivative of x, treat y as a constant. So u of x is going to be 3 over 64 3x plus 4y to the power of 2 times 3. So u of x is equal to 9 over 64 3 of x plus 4y to the power of 2. Now we got to find u of y. U of y, again, chain rule once again, 3 over 64, 3x, as I say, is the same, power of 2, times the derivative of y, so 4. So u of y is equal to 12 over 64, 3x plus 4y to the power of 2. Now we have to go ahead and substitute that into our expression. Let's see, we would have 4 u of x and u of y. We're going to replace u of x and u of y. U of x goes in here, u of y goes in here. So we end up with 4 parentheses 9 over 64, 3x plus 4y to the power of 2. Minus 3, and u of y is 12 over 64, 3x plus 4y squared. Is that equal to 0? Let's distribute the 4, distribute the 3, we get 36 over 64, 3 of x plus 4y to the power of 2, minus 36 over 64, 3 of x plus 4y to the power of 2 is equal to 0. And yes, that is true. Again, those eliminate each other. So in conclusion, this function, u of xy, which is equal to 3x plus 4y divided by 64, to the power of 3 divided by 64, is the solution to our PDE with these constant coefficients and this auxiliary condition. All right, so I hope that helps.